Thanks very much for the kind invitation. So today, what I brought essentially from ICRA here is a talk that I gave in the spatial AI and multimodal AI workshop at ICRA, and also covers a couple of things that we presented there in the main conference, as well as in a couple of workshops. And I put it all under the description of scene graphs in the future of mapping. By the way, if you can't hear me, just now is a good time to indicate. Otherwise, I'll just go ahead. Okay. So what do I want to talk about? Essentially, there have been a couple of different developments in the last 2 to 3 years that are very exciting, and they shift a little bit the landscape of how at least I think about robot mapping in general. So maps, if we think about them as like a general tool that is available to robots, they essentially cover environment-specific information, such as the 3D geometry. If we run reconstruction, we may want to map different object instances, their locations. We need to maybe map free space and kind of different aspects of traversability. And we might also want to remember our path trajectories in these environments. Whereas other aspects of the mission that the robot then performs in these maps actually is environment unspecific, such as locomotion and control, image understanding, ego motion estimation, and so on. That is not really something that we have to keep in maps. Now, we have some interesting kind of new models that we can take as general priors, and robots can just bring with them, and that, for example, is all the kind of common sense reasoning and semantic priors that LLMs, VLMs, and so on bring with us. But then on the other hand, as more and more robotics moves towards mobile manipulation and dynamic environments, there are a couple of additional aspects that we're interested in from our environments. So these are object dynamics, interaction experiences, functional connections. I'll get to that between, for example, light switches and lights, something that you can't really see. You have to gather from experience. And because it's so expensive to gather this information, you want to store it and keep kind of being able to retrieve it later on. And of course, then as we move into environments, something specific is then also user preferences as we, for example, move towards domestic service robots. Okay. And then kind of last 2 years, we now also have these very nice priors on monocular depth or sparse view geometry, models like VGGT, map anything, as well as we'll see, some kind of more generalizable navigation and manipulation skills, kind of models that really generalize well across environments, which, and this is my argument, while we have to change how we do mapping on robots, free up some of the space on this left side. So maybe we don't have to run geometry reconstruction from many different views over SLAM and bundle adjustment anymore, because at any point in time, if we have posed images, we can get very good dense geometry from these multi-view models. And the same that goes for free space and traversability. So there's 3 things that I want to talk about. The first is, what does it mean for SLAM and navigation if we, for example, don't remember reconstruction of our environments anymore? And then the second question is, if we don't need reconstruction, we want to build different kind of maps, how do they look like for applications in mobile manipulation? And I specifically advertise for this formulation of 3D scene graphs. And then I'll finally close with a little bit of an outlook on how we do mapping of physical properties and interactions. So to start with, the first question that we asked ourselves is, how can we do an entire SLAM pipeline without reconstruction at all? And our solution to that is called to go. So kind of PGO, post-rough optimization, but just from 2 views. So we never actually have to triangulate anything. If you think about very regular SLAM, this is kind of how it looks like. You move a camera around in an environment. You kind of can measure some odometry, and then you can try to track or re-identify different landmarks that you see in this environment. And if you gather enough different views, you usually need at least 3, then you can triangulate their spatial position. And if you do this over time, you get a more and more accurate reconstruction of the environment. Now, if you only want to do this from 2 views, obviously you can't just triangulate, but there's a very kind of old concept actually. It started, I think, mostly with like LiDAR SLAM. People talked about post-SLAM. So in post-SLAM, We don't optimize over landmarks or something like this. We essentially still measure odometry, but then we get some kind of external hint that we might have seen something before, and we can essentially just connect two different viewpoints via loop closure edges. So kind of we notice these two cameras are looking at the same thing. We directly get a constraint between them. And of course, we can do stuff like this right now with models like Master, VGT, Map Anything. They exactly do this. Like we give them two views and they can give us a metric relative pose between these two views. And that, of course, sparsifies the whole optimization problem of SLAM quite a lot. And we can build SLAM pipelines with that only do postgraph optimization while still keeping very kind of dense geometric information for all of these different edges. And if we can optimize over that, we essentially get a much sparser problem. So how do we build these edges? There's essentially a couple of different variants that we look for. We could directly build them from Map Anything or a different metric reconstruction model. Most of them are actually not metric, but there are those and we can use them. What we find a bit more stable is that we still use kind of 2D, 3D correspondences out of these models and then run kind of PNP on top of that. It gives a little bit more robustness. And that means we can even take the more classic learned pipeline of 2D matches and lift them to 3D with something like metric 3D or something like that. So many different options that we can try. We can also, of course, always just get scale-free edges without doing any metric estimation. All of these are different ways how we can constrain two different views in our SLAM problem with each other. And then if you deploy this on very long trajectories, something like here, 5 kilometers, 10 kilometers, or something like this, we see that any kind of odometry source that we take as an input, we can actually get very high accuracy, even though we never do any bundle adjustment. And this accuracy, of course, comes from that we can do more loop closures than classical pipelines because models such as VGGT are really good at finding relative constraints between viewpoints that maybe don't have a lot of overlap. And then on the other hand, we get a lot of different edges that are still accurate enough to let us optimize. And we essentially gain very kind of accurate poses. So that means already for just pose estimation and SLAM, we don't necessarily need reconstruction. But then the second question is, usually we need some kind of traversability, free space estimation to move around in an environment. And so if we're moving around, again, if you ask this question, can we do it without any 3D reconstruction? Then one of the things that we looked at is, can we reason about movement from image space? And of course, you may be familiar with works such as vision language navigation that try to learn navigation from vision language models. This here is a little bit more of a kind of classical inspired approach, but I think it learns something quite valuable that we see is extremely useful later on. So what we try to do is we build on these classical approaches for exploration that would do 3D mapping and then frontier extraction, and you can kind of have a sparse set of frontiers. You can decide essentially where your robot should go next if it searches for something or tries to explore the environment. And we bring all of this to the image plane. So essentially we can gather with these 3D mapping approaches a lot of different training data, and then we can train to essentially just detect 3D frontiers from images. And then we can lift them later on, again, with some kind of depth model or a depth that we have available into 3D frontiers. Now, the advantage of this is we essentially learn how frontiers look like in images, but this network that we train here has not only the geometric information of the classical approaches, it can leverage all the visual context of these frontiers. So essentially what we do here is we also get the ground truth on how much would you be able to see if you go to that viewpoint. We can do that in simulation, of course, get a lot of training data from that, and now use the visual context to guess the information gain of each of these frontiers, something that geometric approaches were not able to do before. And from this, we can do these kind of votings and weight the different frontiers with each other. So this is how exploration then looks like in practice. You go somewhere, you see a viewpoint, you kind of lift these frontiers to 3D, and now we can always weight how long does it take to travel to a certain frontier versus what is the informativeness. You see that here kind of given with the size of the different frustums. And so we end up with a kind of very sparse navigation approach, can move around in the environment without actually requiring any reconstruction or actual 3D extraction of frontiers. All of this comes from single images. So how does navigation look like if we don't want to have any kind of reconstruction map at all? Well, we start out from a viewpoint, we maybe detect two frontiers, and we can simply travel to one of that. It's actually in view, so this is kind of just traveling inside what we anyway see. Then we might find a new frontier, we travel to that. Now we don't find any new frontier, that means we have kind of hit a dead end. But of course, we remember there was a viewpoint before from which there was some additional frontier visible. So we have not fully explored the environment. Now in a general metric reconstruction, we would now directly select this as a target and do a planner to find a path over to that frontier. If we don't want to keep any reconstruction in memory because maybe we want to scale to a very large environment, then what we can still do is we can travel back our trajectory to that viewpoint from which we've seen that trajectory, and then we can go visit it. And this is essentially how this looks like here, without keeping any map, just kind of the map here is just for visualization purposes. And of course, you can deploy this easily also on real-world robots. All you need kind of is this network, and then it gives you some sparse 3D frontiers. Now, interestingly, the reconstruction that you see here on the top left is something, if you've ever worked with a spot robot, you know the depth camera in the hand is really low quality because it's for kind of close interaction. Now we just take the RGB camera, and this entire reconstruction that we built here kind of as a post-processing from the images that the robot takes is just made from feedforward depth models. Okay, so what if you don't just want to explore? Again, there's a huge advantage of doing this entire navigation reasoning in image space, and that is that we can, of course, use these frontiers now and use any other kind of visual models to reason about the different detected frontiers. We already have them in image space, and what we can, for example, simply do is make a set of marked prompting to any kind of VLM. We don't need to train this alignment between navigation task and semantic reasoning tasks that VLNs usually need to do. And we can come up with any kind of weighting for any kind of query that we put to the VLM to select the frontier that best matches the query of, for example, go to the living room, leveraging again the whole visual context that is available in the images. And so again, this is how this looks like in practice here. We see on the left kind of the frontiers spawning in 3D space, and the robot starting to explore these. Now here, always skipping kind of different routes because we look for a fire extinguisher and they are not voted high enough by the VLM as something that looks like going to a fire extinguisher. And now we've detected that, so we simply spawn like a last frontier just to move to that object. Now we can take this even one step further. And this is something that we've very recently, this is how the part that I updated now from the ICRA talk, something that we just released a couple of weeks ago, and this is what we call line. So here we in general predict from one image how to move a camera to achieve a certain thing. And that certain thing is, again, kind of just described as a text prompt. So we learn these kind of movements from just egocentric videos that we annotate, just always taking 2 frames, asking what's the difference, how did the camera move? And what we learn now is kind of the opposite. We have a prompt, how do we want the camera to move? And we learn the relative pose. Now this is very interesting because now we can do things like this here, again, without any reconstruction or something like this. We simply say, see what is on the table, and we get a single relative pose of how the camera should move. The camera moves there. And now we can couple this with, of course, other visual models that from just visual space create a certain action or something like this. And in fact, what we see in our experiments is if you couple this together with VLAs that are usually trained on very stationary things and everything should be inside the field of view of the camera, and you now randomize the camera setups a little bit more, we drastically boost performance of these interaction models just by first moving the camera correctly, kind of for them to have everything inside. So kind of here, I find this very interesting because a lot of the navigation research that we've been doing then has also actually a high impact in interactive robotic tasks. Okay, so this, just to wrap up this first part, the kind of things that I want to take out of this, my takeaways from this line of research was that we can solve many navigation tasks without doing any kind of bundle adjustment or dense reconstruction of environments. And that's very relevant because we can now scale these kind of approaches much better to building scale environments, like even kind of whole factory campuses or something like this, because our map representations become much more sparse. And what we also see is that we don't necessarily have to then learn all these navigation tasks end to end, but we have to find really good interfaces, such as relative camera pose or frontiers that we can move to. And these need to be sparse enough such that we can keep them in memory without kind of blowing it up. And of course, all of this is kind of based on that we get really good 3D reconstruction from feedforward models, and we get really robust odometry these days from all the past research that was put in this lab. Okay, so if we go think and say, okay, we now have these much more sparse representations, we maybe don't take a dense reconstruction, then how does the map representation look like that lets us do other useful things? And my answer here to that is that in my research or in our research, we follow a lot this idea of 3D scene graphs that was put out already by others quite some time ago. A big group that does this is also Luca Calone's group from MIT. So essentially, the idea of a scene graph is to have a hierarchical environment representation. We can cluster an indoor scene into rooms, rooms into floors, floors into buildings, and so on and so forth. And our lowest level is usually objects or object parts. So still very sparse. We can, of course, keep potentially some 3D reconstructions for individual parts, but we don't have to have this whole density across the whole environment, and we might even swap in and out parts from the environment. Now, the nice thing about these representations is, for example, that we can query them quite easily with language models. So we can do something like bring me a certain object, and now all I need to do in the scene graph is I need to select a single node inside of this graph. I query this usually with like lib features or something like this. Now I just take the geometry of this node, I run some graph processing, for example, on it, and I can go and manipulate that node. Okay, let's check for the video. Finish. Yeah, there we go. Okay, the other interesting property of scene graphs is that it's very easy to update these representations from dynamic observations. So what we do here is this kind of teach and repeat setting. We track an interaction through meta-aria glasses, so these smart glasses that give us egocentric data. And if we maybe look once more, then we see if we have a good tracking that we kind of show in this work, then we can very easily update these representations, because all it takes is just updating a couple of pose parameters of one node in this graph. Much easier than it would be for these more dense representations. Now, something that we showed at ICRA is that another nice property of scene graphs is that they are very nice to integrate with LLMs. Without, again, any kind of training or something like this, we can usually process a scene graph into a JSON representation that really simply has the graph information without any geometry. And because these representations are quite sparse, we can usually fit them or make them fit inside the context window of just a single query, which allows us to do very complex queries, of course, that go beyond just retrieval through clip descriptors or something like this. And we can kind of just get responses out of like target nodes or something like this. And because we can couple this still kind of in the back end with kind of more metric representations or some kind of other navigation framework, we can easily navigate there. And that is a task that we can use just classical methods. We don't need any VLM for that or LLM. Now, the interesting property of that is because we can leverage the entire semantic priors and reasoning capabilities of LLMs, that we can locate objects in these maps that have actually been relocated. So let's say we have a first mapping session, then we move around a couple of different objects, something that happens every day in every household that a robot should operate in. Now, of course, a classical mapping framework would allow us to revisit the last location that we've seen that object, but by essentially processing this entire thing through the semantic priors of LLMs, we can, of course, easily guess also other likely locations where that object might be. And that even holds for objects that were not present at all during the mapping session. So something that, again, like these classic retrieval approaches, I just search for the objects that I have in my map, wouldn't work at all for that because there's nothing to retrieve. Still, the context actually provides us with a good enough guess to find these objects that have not been mapped at all before. Then something that kind of goes now beyond like these classical semantic mappings of objects and so on, as I already said, we can build connections now in these graphs that have nothing to do with any kind of appearance. So a very classical problem for this is you come into a room and you try to figure out which light is operated by which light switch. Now, no VLM in the world can really tell you because these are highly random and not even cultural or something like this. There's no central rule to it. You can very simply find this out, however, by trying out in the environment. So this is, of course, something we can do with robots by interacting with the different light switches, observing the different lamps. And now scene graphs allow us, of course, give us a very good structure to build connections and simply just connect two nodes with these kind of functional connections. So this is, again, a map representation that allows us to include that additional information very easily. Now, to close off, there's a couple of other physical properties that I am very interested in the future to put, again, into these kind of representations. And this is just something that I don't have the solution yet, but we at least now started to collect data that we can use for these kind of mapping tasks. And it's something I want to advertise a little bit. It's called the HOI dataset. HOI, like saying hi in Switzerland, but also like hand-object interaction. So we have a lot of these interactions, for example, with these grippers here, but also with human hands. And we measure different, all kinds of different things, tactile sensing. And one of the things that I'm most interested in is the modality of interaction forces. So we have these couple of different cabinets and ovens and so on. And we know, of course, as humans, that to operate each of these, you need different kind of force profiles. Now, this is something that we, for the first time, measured. I think this is something, again, that is environment-specific information that is super relevant for robots to kind of store, that you remember, okay, you need to apply a little bit more force here. For this kind of cabinet, it's fine. For another cabinet, if you apply that kind of force, probably something is stuck, and you should not do that because you might break something. Now, in this data set, we give you essentially a lot of different interactions. We give you 3 different gripping modalities. We have a couple of robot demonstrations. We give you ego and exocentric views. So I think there's a lot of playground to play around with these kind of future information that we want to put into robotic maps. Now, to conclude all of this, what I started out with is arguing that we can free up some of the space that we so far kept as environment-specific information in maps such as 3D geometry and really dense free space information. And I've shown that there's ways how we can leverage rather generalizing models, priors that robots can bring with them to ad hoc create that kind of information if we really need it, but we don't need to store it all the time. And our maps can kind of rather free up that memory to then store interesting other kind of information, such as object dynamics, interaction experiences, functional connection. And I think something that might be super interesting in the future are also user preferences. With this, I want to thank all my collaborators that actually did the work that I've presented here, both at ETH and the University of Bonn. I'm happy to take some questions. I also put my email here in case you have any follow-ups later on.
you.